Have you ever wondered what happens inside a molecule when light interacts with it? In today's video, we're diving into the fascinating world of UV visible spectroscopy, a technique that reveals how molecules absorb light and transitions between different electronic states. Inside every molecule, electrons occupy specific energy levels called molecular orbitals, such as sigma, pi, and non-bonding orbitals. Above this lie higher energy antibonding orbitals like sigma star and pi star. When UV or visible light shines on a molecule, its electrons may jump from a lower energy orbital to a higher one. But this can only happen if the energy of the incoming photon exactly matches the energy gap between these two orbitals. If the photon's energy doesn't align with this gap, the molecule simply would not absorb it. However, even when the energy does match, not all transitions are allowed. Molecules follow strict selection rules. Common allowed transitions include pi to pi star and n to pi star, which gives rise to the characteristics peaks in UV spectra. Some transitions, especially those involving changes in electron spin, like going from a singlet ground state to a triplet excited state, are forbidden or occur only with very low intensity. In a typical singlet ground state, electron spins are paired. Excitation can keep them paired in a single excited state, or much less commonly lead to a triplet state through so-called intersystem crossing, where the spins become parallel, just like you see here in this picture. Let's explore how UV visible spectrometer actually works by following the path of light through the instrument. Everything begins at the light source, which is typically a deuterium lamp for UV wavelengths and a tungsten-halogen lamp for the visible region. This lamp produces a broad continuum of light containing all the wavelengths the instrument may need, everything. From here, the light first encounters the entrance slit, the component responsible for controlling how much light enters the optical system. The entrance slit also plays a critical role in determining the resolution of the monochromator by shaping the beam before its dispersion. Next, the shaped beam enters the monochromator, usually built around a prism, or sometimes we call it diffraction grating. Inside the monochromator, incoming broadband light is dispersed into its component wavelengths. By rotating the grating, the instrument selects only one narrow wavelength at a time. Only one. These isolated wavelengths then exit through the exit slit, forming a single wavelength beam used for analysis. Once the light is monochromated, it reaches the beam splitter. At this stage, the beam splitter has a crucial job. It divides the single wavelength beam into two identical beams. One beam travels towards the sample cuvette, while the other is directed towards the reference cuvette. This is what defines a dual beam UV-vis spectrometer. The sample cuvette contains the analyte and may absorb part of the incoming light, while the reference cuvette contains the pure solvent. The solvent which was analyte was dissolved into, and that solvent to account for background absorption. Using two beams allow the instrument to automatically subtract the signals coming out of the sample and other potential sources of noise. After passing through the respective cuvettes, each beam that passed the reference and the sample cuvette reached the detector, where the transmitted light intensities from the both samples and the reference paths are collected for further analysis. These detectors convert the light intensity into electrical signals, which are then sent to the computer. Finally, the computer and data system compare the signals from the sample and reference beams. The software uses the absorbance values to plot a spectrum of absorbance versus wavelengths, generating the final UV-Vis spectrum that reveals the electronic transitions occurring in the molecule.